Look up on a clear night, far from any city, and you will see a pale river of light cutting across the darkness. For most of human history, nobody knew what it was. Some cultures called it a road for the dead. Others called it spilled milk from a goddess's breast. It took us thousands of years to understand that we were looking at our own home from the inside. 100 billion stars, seen edge on, so densely packed that their individual light blurs into a single glowing band. We call it the Milky Way. And here is the question this documentary is built around. The one that will follow us through every chapter that comes after it. If we ever found a way to leave our solar system behind entirely, to cross the vast nothing between stars and reach another sun, could we ever go further than that? Could humanity, or anything descended from humanity, actually leave the galaxy itself? The honest answer, based on what physics currently tells us, is almost certainly no. Not in any time frame that resembles a human future. Not with any technology we can presently imagine, and arguably not with any technology that the laws of this universe will ever permit. That is not a comfortable thing to say at the start of a documentary. And we are not going to leave it there. Because the reasons why are far stranger, far more interesting, and far more revealing about our place in the cosmos than the simple word no suggests. To understand why leaving the galaxy may be permanently beyond our reach, we first have to understand something most people never stop to consider: the difference between leaving home and leaving the neighborhood. We have already technically left home. 4 spacecraft have crossed the boundary of our solar system and entered interstellar space. It sounds like the hardest part should be over. It isn't. It's the smallest possible first step in a staircase that may not have a top. So let's begin there, with the boundary we've already crossed, because understanding exactly what we accomplished and exactly how little it actually represents is the only way to grasp the true scale of what comes next. In 1977, 2 spacecraft left Earth within weeks of each other. Voyager 1 and Voyager 2 were never designed to leave the solar system. Their mission was to fly past Jupiter and Saturn, take pictures, measure magnetic fields, and finish their work within a few years. Nobody expected them to still be transmitting data nearly 5 decades later. And nobody expected them to become the first human-made objects to cross into the space between stars. But something happened along the way. The gravity of the outer planets, used correctly, can fling a spacecraft outward at extraordinary speed. A maneuver called a gravity assist, essentially stealing a tiny fraction of a planet's own orbital momentum and handing it to the spacecraft for free. Voyager 2 used Jupiter, then Saturn, then Uranus, then Neptune. Each flyby adding speed the spacecraft could never have achieved on its own fuel. Voyager 1 used a more direct, faster route past Jupiter and Saturn alone. By the time they finished their planetary tour, both spacecraft were moving fast enough to never come back. They were leaving for good. It would take Voyager 1 35 years to reach the edge of the Sun's influence. 35 years to cross a boundary scientists call the heliopause, the point where the solar wind, the constant outward breath of charged particles streaming from our Sun, finally grows too weak to push back against the thin gas drifting between the stars. Beyond the heliopause, you are no longer in the Sun's bubble. You are in the galaxy proper. Voyager 1 crossed that boundary in 2012. Voyager 2 followed in 2018. This is usually where the story is told as a triumph, and it is one. But here is the detail that almost never gets the attention it deserves. even after 35 years of travel. Even after using the gravity of 4 planets to build up speed, Voyager 1 had only escaped our Sun's immediate influence. It had not gone anywhere, relatively speaking. It remains, even now, far closer to our Sun than our Sun is to its nearest stellar neighbor. At its current speed, Voyager 1 would need roughly 73,000 years just to cover the distance to Alpha Centauri. And it isn't even headed there. It is on a trajectory that will take it nowhere near any star for a very long time. Sit with that number for a moment, because everything else in this documentary depends on truly feeling it rather than just hearing it. 73,000 years is longer than the entire span of recorded human civilization. Multiplied roughly 10 times over, it is longer than the time since modern humans first painted on cave walls in Europe. It is a span of time so large that comparing it to a human lifetime doesn't even produce a useful number. It produces something closer to a wall. And Alpha Centauri is the closest star system to our own. This is the easy case. This is the best case scenario for interstellar travel using anything resembling the technology that exists today. If reaching our nearest neighboring star is this difficult, what does that suggest about reaching the edge of our own galaxy? A galaxy that is, by current measurements, somewhere in the range of 100,000 light-years across. This is the moment the documentary needs to slow down, because numbers this large stop meaning anything unless we rebuild them from the ground up. A light-year is not a measurement of time, despite how the name sounds. It's a measurement of distance. Specifically, the distance light travels in a single year, moving at roughly 186,000 miles every second. Light is the fastest thing in the universe. Nothing with mass can move as fast as light. And as far as we currently understand physics, nothing ever will. So when astronomers say a star is 4 light-years away, they mean that light from that star, moving at the absolute speed limit of the universe, takes 4 full years to make the trip. Our Sun's light takes about 8 minutes to reach Earth. That's how close we are to our own star. On a cosmic scale, 8 light minutes. Alpha Centauri is roughly 4 light-years away. To grasp what that actually means, look up at it on a clear night. It's visible low in the southern sky if you're far enough south, one of the brightest points of light out there. The light hitting your eyes left that star around the time certain major world headlines from your own teenage years or your parents were unfolding. That photon began its silent journey through cold and empty space years before it reached the back of your eye tonight. Now stretch that same idea across the galaxy. Our solar system sits roughly 26,000 light-years from the center of the Milky Way, out in one of the spiral arms, in what astronomers sometimes call, almost affectionately, suburbia. The galaxy itself spans somewhere between 100,000 and 180,000 light-years from edge to edge, depending on exactly where you decide the faint outer disk actually ends. Even the most conservative measurement means that light, again, the fastest thing that exists, would need 100,000 years to cross from one side of our galaxy to the other. 100,000 years for light. Not for a spacecraft, not for a human being. For light itself, racing at the one true speed limit of this universe. This is the first real moment of this documentary, and it deserves to be felt rather than rushed past. We are not talking about a long journey in the way a flight from one continent to another is a long journey. We are talking about a journey so vast that the unit we use to measure it, the year it takes light to travel, becomes the smallest meaningful currency, and we still need 100,000 of them just to cross the room we live in. So why does this matter for the future of humanity? Why should anyone watching this documentary care whether we could ever leave the Milky Way when we haven't even reached another star? Because the question of leaving the galaxy is really a question about limits, about what is physically possible for any civilization, no matter how advanced, no matter how much time it has, no matter how clever its engineering becomes. And the answer to that question, once we trace it all the way down to its foundations, tells us something profound about the kind of universe we actually live in. A universe that may be quietly, permanently, structured to keep galaxies isolated from one another, the way islands were isolated by oceans before ships existed. Except this time, there may never be a ship capable of crossing. To understand why, we have to leave the question of distance for a moment and ask a more fundamental one. What would it actually take, physically, to cross interstellar distances at all? Because everything about leaving the galaxy depends on first answering whether we can leave the solar system in any meaningful, repeatable way. And that alone reveals just how steep this staircase truly is. Start with the engines we actually have. Chemical rockets, the kind that have launched every human being who has ever left Earth's surface, work by burning fuel and expelling the exhaust at high speed, pushing the rocket forward by Newton's third law. Every action has an equal and opposite reaction. It's the same principle by which a fire extinguisher can push you backward across a frictionless floor if you set it off facing away from you. Chemical rockets are extraordinarily good at lifting heavy objects out of a planet's gravity well in a short, violent burst. They are spectacularly bad at sustained acceleration across the emptiness between stars, because they have to carry every drop of fuel they will ever use. And the fuel itself has mass, which requires more fuel to move, in a spiral of diminishing returns that engineers call the tyranny of the rocket equation. Voyager 1, the fastest moving human-made object for most of its journey, travels at about 38,000 miles per hour relative to the Sun. That sounds extraordinary, and it is by the standards of anything built before the spacecraft. But the speed of light is roughly 670 million miles per hour. Voyager 1's speed is a rounding error compared to light speed, less than 0.02% of it. At that pace, as we said, Alpha Centauri is 73,000 years away. So the obvious next question becomes, could we simply build something faster? The answer, encouragingly, is yes, to a point. Engineers and physicists have spent decades designing concepts that could move dramatically faster than any chemical rocket. Nuclear thermal propulsion, which uses a reactor to superheat propellant rather than burning chemical fuel, could in theory roughly double or triple the efficiency of a conventional rocket. Nuclear pulse propulsion, the famous and slightly unsettling Project Orion concept from the 1950s and 60s, proposed detonating small nuclear explosives behind a heavily shielded pusher plate, riding the shockwaves forward like a surfer, riding a wave, in principle, reaching several percent of the speed of light. Ion engines, which are already flying on real spacecraft today, accelerate charged particles using electric fields rather than combustion, achieving far higher exhaust velocities than chemical engines, but producing thrust so gentle that it takes months of continuous firing to build up speed that a chemical rocket reaches in minutes. Then there are the concepts that exist only on paper, at the very edge of engineering plausibility. Solar sails, vast and impossibly thin sheets of reflective material, pushed not by fuel but by the gentle pressure of photons themselves, or by a powerful laser beamed from near Earth. A concept seriously studied under the name Breakthrough Starshot, aiming to accelerate a postage stamp-sized probe to perhaps 20% of light speed, using a ground-based laser array, delivering an enormous focused pulse of energy. Antimatter engines, which would convert mass directly into energy with perfect efficiency. Assuming we could ever produce and safely store antimatter in any meaningful quantity, which at present we cannot, not by many, many orders of magnitude. Fusion rockets, harnessing the same reaction that powers the sun, promising far greater efficiency than fission or chemical engines. Assuming we ever achieve sustained, controllable fusion at all, a goal that has remained tantalizingly out of reach since serious research began in the 1950s. Each of these concepts, on paper, chips away at the 73,000-year wall. A laser-driven sail at 20% of light speed could reach Alpha Centauri in roughly 20 years, rather than 70,000. That's not a small improvement. That's the difference between an idea passed down through 3,000 generations and a journey a single human being could undertake and survive to see completed. So here, for a moment, the documentary wants to feel optimistic. 20 years to the nearest star, using nothing but a sufficiently powerful laser and a very thin sail, is within the outer edges of plausible future engineering. It is the kind of number serious physicists are willing to publish papers about. But notice what just happened in that sentence. We solved the problem of reaching the nearest star. Only the nearest star, only with a probe the size of a postage stamp, with no astronauts, no return trip, no scientific instruments beyond the absolute minimum, and using an amount of energy that would require infrastructure we have not yet built and may not build for generations. And even granting all of that, even being as generous as possible, 20 years gets us to one star. The galaxy contains, by current estimates, somewhere between 100 billion and 400 billion stars. Most of them are not 4 light years away. Most of them are thousands or tens of thousands of light years away. The same laser sail concept that reaches Alpha Centauri in 20 years would take 5,000 years to cross a mere 1,000 light years. A distance that, on the scale of the galaxy, is still essentially our own backyard. This is where the second curiosity loop of this documentary opens quietly beneath the first. Even our most optimistic, almost science-fictional propulsion concepts only solve the easiest version of the problem. They get us across the narrowest gaps. They do nothing to solve the deeper one. And the deeper one is not really about engines at all. It's about time, and what time does to anything that tries to move through it for too long. Here is the uncomfortable truth that science fiction rarely lingers on. Speed is not actually the central obstacle to interstellar and intergalactic travel. Duration is. And duration interacts with something far more unforgiving than fuel efficiency. It interacts with the lifespan of whatever or whoever is doing the traveling. A human being lives at best around a century. A spacecraft, even a well-built one, faces a different but related problem. Every system on board, every wire, every seal, every piece of electronics, every joint is subject to slow degradation from radiation, micrometeorite impacts, thermal cycling, and the simple, patient work of entropy. Voyager 1 has survived nearly 50 years, partly because its instruments were built with an almost paranoid level of redundancy, and partly because deep space, while hostile, is also strangely gentle in certain ways. There's no weather, no corrosion from oxygen, no biological decay. But Voyager's plutonium power source is fading. Within the next several years, its instruments will begin shutting down one by one, simply because there won't be enough power left to run them. A spacecraft, however well engineered, is not immortal. It has a clock built into its very materials. If reaching even the nearest stars takes decades, using our most optimistic technology, and reaching anywhere meaningful across the galaxy takes thousands or tens of thousands of years, using anything we can presently imagine, then any vessel attempting that journey has to solve a problem that has nothing to do with rocket science at all. How do you keep something, or someone, functioning, intact, and purposeful across a span of time that dwarfs the lifespan span of every system, biological or mechanical, that we know how to build? This is the point where the conversation about interstellar travel usually splits into a handful of proposed solutions, each more strange than the last, and each carrying its own unresolved problems. The first idea is the generation ship. A vessel large enough to be a self-contained world, carrying not a handful of astronauts, but an entire functioning community, who would live, raise children, grow old, and die aboard the ship, with their descendants, many generations later, finally arriving at the destination their ancestors never saw. It is, in a very real sense, a one-way migration across time. As much as space, it requires solving problems we have never solved on Earth, let alone in a sealed metal vessel drifting through radiation-soaked vacuum, a fully closed ecological system that recycles air, water, and food indefinitely without resupply. A society stable enough to survive cultural drift, conflict, and the psychological weight of knowing that home is something only the original crew ever actually experienced firsthand, and engineering robust enough to function not for years, but for centuries, without the possibility of replacement parts shipped from Earth. The second idea is suspended animation, sometimes called hibernation travel. Placing the crew into a state of drastically slowed metabolism, perhaps even something approaching true biological stasis, so that subjective time passes far more slowly than time outside the body. This idea appears constantly in fiction because it elegantly sidesteps the generation ship problem. The trouble is that human biology has no known mechanism for safely entering deep extended stasis. Some animals hibernate for months. None do anything remotely close to what would be required for a journey of decades or centuries. And the medical science needed to attempt this in humans remains, as of now, entirely theoretical. The third idea, more radical still, abandons biological humans traveling at all in favor of digital minds. The proposal that a future civilization might map human consciousness in enough detail to transfer it into a computational substrate, then send that substrate across the stars in a much smaller, much more durable probe, free from the need for food, air, gravity, or a lifespan measured in mere decades. This concept depends entirely on a question we cannot currently answer: whether consciousness, identity, and continuity of self can exist meaningfully and authentically inside a machine. It remains, today, philosophy wearing the costume of engineering. And the fourth idea is the one that sounds the most like magic and is treated by physicists with the most caution, somehow slowing the effective passage of time for the travelers relative to the universe outside, so that a journey of thousands of years, from the perspective of someone watching from Earth, might feel like only a few years to those making the trip. This is not science fiction. This is a real, measured, repeatedly confirmed feature of how time actually behaves in this universe. And it is the next thread this documentary needs to pull, because it leads somewhere genuinely strange. In the early 20th century, a young physicist working in a Swiss patent office began questioning an assumption almost everyone before him had taken for granted: that time flows at the same rate, everywhere for everyone, regardless of how fast they happen to be moving. Albert Einstein's special theory of relativity, published in 1905, demonstrated something the human mind finds almost impossible to intuitively accept: that time is not a fixed backdrop against which the universe unfolds. Time is flexible. It bends, stretches, and slows, depending on how fast you are moving relative to something else, and depending on how deep you are sitting inside a gravitational field. This is not a hypothesis awaiting confirmation. It has been tested repeatedly with extraordinary precision. Atomic clocks flown on airplanes register, when they land, a measurably different elapsed time than identical clocks that stayed on the ground. A difference of mere billionths of a second, but a real, repeatedly measured difference, exactly matching what Einstein's equations predict. The global positioning system satellites orbiting Earth right now have to correct for this effect constantly. If engineers ignored relativistic time dilation, GPS coordinates would drift by miles within a single day, because the satellites, moving fast and sitting in a weaker gravitational field than the surface of Earth, experience time at a very slightly different rate than we do. The effect at everyday speeds is vanishingly small, but the closer an object's speed gets to the speed of light, the more dramatic the effect becomes. Not gradually, but in a way that accelerates sharply as you approach that ultimate cosmic limit. A spacecraft moving at 50% of light speed would experience time passing at roughly 87% of the rate experienced by someone standing still. Move at 90% of light speed, and the traveler's clock slows to less than half the outside rate. Move at 99% of light speed, and time for the traveler slows to roughly 1/7 of the outside rate. Push to 99.9%, and the ratio becomes more than 20-to-1. This means, in principle, that a spacecraft capable of sustaining extremely high fractions of light speed could allow its crew to experience a journey across thousands of light years in what feels, to them, like only a handful of years, even though, to everyone they left behind on Earth, thousands of years would pass before the ship reached its destination, and thousands more before any message could possibly return. This is the moment the documentary needs to sit with the genuine wonder of this idea, before showing why it doesn't actually solve our problem. Imagine for a moment a crew that departs Earth on a ship, somehow capable of reaching 99.9% of light speed, itself an engineering feat with no known solution. But let's imagine it for the sake of understanding the physics. To that crew, a journey across 10,000 light years might feel like only a few decades of subjective, lived time. They could grow old slowly, perhaps even live to see the far end of the journey. Time dilation, in this sense, genuinely could make interstellar and even intergalactic distances survivable for the individual traveler. But notice precisely what this solves and precisely what it does not. It solves the problem of the traveler's experience. It does nothing whatsoever to solve the problem of Earth's experience. While the crew ages only decades, 10,000 years pass for everyone and everything they left behind. Civilizations rise and fall in that time. Languages change beyond recognition. The very idea of returning home becomes meaningless, because the home that existed when they departed will have been gone, transformed beyond recognition, for longer than the entire span of recorded human history. There is no message you could send back that would arrive while anyone who remembered you was alive to receive it. There is no negotiating a round trip in any sense a human being currently understands the word. Time dilation does not shrink the universe. It only changes whose clock you choose to suffer the consequences on. And this points towards something this documentary will return to, again and again. Nearly every proposed solution to interstellar and intergalactic travel works by trading one impossible problem for a different, almost as impossible one. Faster engines solve speed, but create catastrophic energy requirements. Generation ships solve duration, but create unsolved problems in closed ecosystem biology and multi-century social stability. Suspended animation solves the felt experience of duration, but depends on biology we don't currently understand and may never achieve. Time dilation solves the traveler's lived experience, but permanently severs any connection to the civilization that sent them. There is no version of this problem, examined honestly, that simply goes away. There is only a menu of different, equally enormous costs, and we have, so far, only been discussing the challenge of crossing distances within our own galaxy. Distances measured in thousands or, at most, tens of thousands of light years. The Milky Way itself, edge to edge, requires that 100,000-year journey for light alone. But the question this documentary is built around isn't whether we could ever reach another star within our galaxy. It's whether we could ever leave the galaxy entirely. And the distances involved in that question make everything we've discussed so far look, almost laughably, like a warm-up exercise. Our galaxy is not alone in the universe. It is part of a small, gravitationally bound cluster of galaxies called the Local Group, which includes our Milky Way, the slightly larger Andromeda galaxy, the smaller Triangulum galaxy, and roughly 80 additional dwarf galaxies, most of them faint, small, and gravitationally tied to one of the two larger members. Andromeda, our nearest large galactic neighbor, sits roughly 2.5 million light-years away. Read that number again, slowly, because it deserves to land with its full weight. 2.5 million light-years, not 2,500. Not 2,500,000. 2.5 million, if reaching a star within our own galaxy at 20% of light speed, itself an almost fictional engineering achievement, takes decades to centuries, depending on distance, and crossing 1,000 light years at that same speed takes 5,000 years. Then crossing 2.5 million light years, even at that same generous 20% of light speed, would take roughly 12.5 million years. 12.5 million years is longer than the entire existence of the human species. It is longer than the time since our evolutionary lineage split from the ancestors of chimpanzees. It stretches back to an era before most of the animal species alive today existed in anything like their current form. And Andromeda is our closest major galactic neighbor. It is, relatively speaking, right next door, gravitationally bound to us as part of the same small cosmic neighborhood. Beyond the local group, the distances grow almost incomprehensibly larger still. Tens of millions, hundreds of millions, billions of light years to other galaxy clusters scattered across the observable universe. This is the moment in the documentary where the question shifts. We are no longer asking, is this hard? We are asking something closer to, is this even the right kind of question? Because at a certain point, distances stop being an engineering problem and start becoming something closer to a fact about the structure of reality itself. A fact that no amount of cleverness, no future technology, no 1,000-year civilizational project can simply engineer its way around. And this is where the documentary needs to introduce something that very few popular explanations of space travel ever properly address. The universe itself is not standing still while we try to cross it. It is expanding. And that expansion is not a minor detail. It may be the single largest reason why leaving our galaxy, or any galaxy, might be permanently, physically impossible, regardless of how advanced any civilization ever becomes. In the 1920s, an American astronomer named Edwin Hubble, working with what was then the largest telescope in the world, atop a mountain outside Los Angeles, noticed something deeply strange about distant galaxies. Their light was shifted toward the red end of the spectrum, and the farther away a galaxy was, the more dramatically red-shifted its light appeared. Hubble correctly interpreted this as evidence that those galaxies were moving away from us, and that the speed of their recession increased the farther away they were. This became known as Hubble's law, and it remains one of the foundational observations of modern cosmology. The conclusion that followed from this observation reshaped our entire understanding of the universe. Space itself is expanding, not galaxies flying apart through static space like shrapnel from an explosion, but the literal fabric of space. The distance between essentially every point and every other point, not gravitationally bound together, is continuously stretching everywhere, all the time. This is genuinely one of the strangest facts in all of physics, and it's worth pausing here to make sure it lands correctly, because it is very easy to misunderstand. The expansion of the universe does not mean galaxies are moving through space the way a rocket moves through space, propelled by some force, pushing them outward from a central point. There is no center. There is no explosion radiating outward into empty space that was already there. Space itself, the very medium through which light and matter travel, is increasing in volume, everywhere, simultaneously, like a loaf of raisin bread rising in an oven where every raisin moves from every other raisin, not because the raisins are crawling through the dough, but because the dough itself is expanding between them. This means something profound for the question of intergalactic travel. It isn't just that Andromeda is 2.5 million light-years away right now. It's that the distance between us and Andromeda, and between us and every other galaxy not gravitationally bound to our local group, is continuously increasing, even as you watch this documentary, even as nothing physically moves anywhere at all. For relatively nearby galaxies within and near our local group, the expansion of the universe is currently overwhelmed by local gravity. Andromeda, in fact, is gravitationally bound closely enough to our galaxy that it is actually moving toward us, not away. and the two galaxies are expected to begin merging in a few billion years. A gravity winning locally against the broader cosmic expansion. The local group as a whole is gravitationally bound tightly enough that the galaxies within it are not, on the whole, drifting apart due to cosmic expansion. But beyond the local group, beyond galaxies bound to us by mutual gravity, the picture changes entirely. Galaxy clusters far beyond our own gravitational reach are not just far away. They are getting farther away continuously, and the rate at which they recede increases the farther out you look. This is described by a number cosmologists call the Hubble constant, which essentially tells you how many additional miles per second a galaxy appears to recede from us for every additional unit of distance separating us. And here is the detail that turns this from an obstacle into something closer to a hard physical boundary. Because the recession speed increases with distance, there exists a distance far beyond the edge of our own galaxy, but very much within the observable universe, at which a galaxy's apparent recession speed, driven purely by the expansion of space itself, exceeds the speed of light. This does not violate Einstein's physics, despite how it sounds. Nothing is moving through space faster than light. Space itself is expanding, and the combined effect of countless tiny expansions stacked across enormous distances can add up to an effective separation speed greater than light. Without any single object, anywhere, locally moving faster than light relative to the space immediately around it. It's a subtle distinction, but a real and mathematically rigorous one. And it has an absolutely staggering consequence. There are galaxies in the observable universe right now, whose light reaching us today was emitted before the expansion of space accelerated their recession beyond the speed of light, meaning any light or any signal or any spacecraft we might someday send could never reach them, not because we lack the technology, because the space between us and them is growing faster than anything could ever cross it, no matter how fast it travels, even at the absolute speed limit of the universe itself. This is the single most important idea in this entire documentary, and it deserves to be stated plainly. There may be galaxies that are, right now, permanently unreachable, not because of any limitation in our engineering, but because of the literal geometry and expansion rate of the universe itself. No civilization, however advanced, however patient, however many millions of years it has to work with, could ever send anything to those galaxies and have it arrive. The distance between us and them is widening faster than the fastest possible thing in existence could close the gap. Our own Milky Way does not yet sit beyond this boundary relative to most of its immediate surroundings. We are still gravitationally bound to our local group, still capable, in principle, of crossing to Andromeda given enough time, and a sufficiently advanced civilization willing to spend millions of years on the project. But the deeper question this raises is almost more unsettling than a simple yes or no about whether we could leave our own galaxy. It suggests that the universe itself may be quietly, continuously closing doors. Galaxies that were once close enough to reach, in principle, given enough time, and a sufficiently determined civilization, may slip beyond that boundary as cosmic expansion continues to accelerate. And here is where this documentary needs to introduce its next layer, because the expansion of the universe is not just continuing, it is accelerating. In the late 1990s, two independent teams of astronomers studying the light from distant exploding stars called Type Ia supernovae made a discovery so unexpected that it initially seemed like a measurement error. Distant supernovae appeared dimmer than they should have been if the universe were expanding at a constant rate, or even slowing down due to gravity, as most physicists at the time expected. The only explanation that fit the data was one nobody had been looking for. The expansion of the universe is speeding up, not just continuing, accelerating. This discovery, confirmed by multiple independent lines of evidence in the years since, led to the identification of what cosmologists now call dark energy, a mysterious property of empty space itself that appears to be driving this acceleration. We do not currently know what dark energy actually is. We know how it behaves. We can measure its effects with considerable precision, and by current estimates, it makes up roughly 70% of all the energy content of the universe. But its fundamental nature remains one of the deepest open questions in all of physics. What dark energy means, practically, for the questions this documentary set out to answer, is this. Not only are distant galaxies receding from us, and not only does that recession speed increase with distance, but the rate of that acceleration is itself increasing over cosmic time. The universe is not settling into some final, fixed, comprehensible shape. It is continuously expanding faster, which means the boundary beyond which nothing can ever reach us, and beyond which we could never reach anything, is continuously creeping inward, swallowing galaxies that might once have been reachable, removing them permanently from any future civilization's potential grasp. This single fact reframes everything we discussed earlier about engines, fuel, time dilation, and generation ships. Even if humanity solved every engineering problem we've described, even if some future civilization built ships capable of sustaining 99.99% of light speed, capable of supporting crews or digital minds across millions of years of subjective or dilated time, there would still exist a hard boundary, set not by engineering, but by the fundamental expansion rate of space-time itself, beyond which travel becomes not merely difficult, but mathematically, physically impossible. This is sometimes called, among cosmologists, the cosmic event horizon, not to be confused with the event horizon of a black hole, though the underlying logic carries a strange family resemblance. In both cases, it marks a boundary beyond which no signal, no light, no information, and certainly no spacecraft can ever cross to reach us, nor could anything of ours ever cross to reach them. For a black hole, that boundary is set by gravity so intense that not even light can escape. For the universe as a whole, the boundary is set by the accelerating expansion of space itself, stretching the gap between here and there faster than light could ever close it. So we arrive, fairly early in this documentary, at an answer that is genuinely unsettling and worth letting sit in the silence for a moment before we continue. It is entirely possible, supported by mainstream, well-tested cosmological models, not speculative fringe physics, that the overwhelming majority of galaxies in the observable universe are already permanently beyond the reach of anything we, or any civilization descended from us, could ever build or send. Not because we are not clever enough, not because we have not had enough time, but because the geometry of the universe itself has already decided the answer, long before any civilization capable of asking the question ever evolved to ask it. And yet, and this is important, because despair is not actually what this documentary is interested in producing, our own galaxy, and our own local group may represent a meaningfully different case. Because we are gravitationally bound to Andromeda and our other nearby neighbors. The question of whether we could someday reach them is not foreclosed by cosmic expansion in the same absolute way. It remains, instead, an engineering and civilizational question rather than a purely cosmological one, which means the real frontier of this documentary's question isn't actually, could we leave the universe? It's something slightly smaller, slightly more grounded, and in some ways slightly more haunting. Could we, or could anything descended from us, ever leave the Milky Way and reach even our closest neighboring galaxy? And if even that proves to be beyond what any civilization could realistically achieve, what does that tell us about the true shape of the box we live inside? To answer that, we need to go further than distance and propulsion. We need to understand what actually happens to a human body, a human mind, and a human society across the kind of timescales these journeys would require. Because even if every engineering problem was solved tomorrow, the deepest barrier to leaving the galaxy might not be physics at all. It might be us. Consider for a moment what a multi-thousand-year voyage would actually demand of the people, or the descendants of people, making it. A generation ship traveling for 10,000 years would need to maintain a closed ecological system, stable enough to recycle air, water, and nutrients indefinitely, with zero possibility of resupply, for roughly 400 consecutive human generations. To put that in perspective, the entire span of recorded human history, every empire, every war, every technological revolution, from the invention of writing to the invention of the internet, covers perhaps 200 to 250 generations. A single generation ship voyage to even a relatively close star, let alone another galaxy, would need to outlast the entirety of recorded human civilization. Twice over, while never failing, never running out of a single critical resource, and never losing the social cohesion required to keep a closed community functioning across that unimaginable span. We have never built a closed ecological system on Earth that has remained stable for more than a few years, let alone centuries. Biosphere 2, an experimental sealed facility built in the Arizona desert in the early 1990s, was designed to test exactly this kind of self-sustaining environment. Within months, oxygen levels began dropping unexpectedly. Crop yields fluctuated wildly, and unplanned ecological imbalances, including an explosion in cockroach and ant populations that outcompeted other species, forced researchers to pump in supplemental oxygen, compromising the experiment's central premise. If maintaining ecological balance proves this difficult across a few years on Earth, with the entire planet's scientific infrastructure available to troubleshoot problems in real time, maintaining it for centuries inside a sealed vessel drifting through deep space, with no possibility of outside help, represents an engineering challenge that may be every bit as daunting as the propulsion problem we started with. And then there is the social dimension, which is in some ways even less tractable than the biological one. Could a community of humans, or their descendants, actually remain stable, purposeful, and cooperative across hundreds of generations, confined to a finite enclosed space, with no contact with the outside world beyond what their ancestors could remember, and what their descendants could only imagine? Human societies on Earth, with the entire planet to expand into, with abundant resources, and with constant contact with other societies, have nonetheless experienced civil wars, revolutions, religious schisms, and catastrophic breakdowns of social order repeatedly throughout history. There is no guarantee. Arguably, there is very little historical evidence to even suggest the possibility that a community sealed inside a metal vessel for 400 generations would remain functional, let alone committed to a mission whose original purpose its members, many generations removed from the launch, might come to question, resent, or simply forget. This is not a minor footnote to the engineering problem. It may be the central problem. A spacecraft is, in the end, only as durable as the civilization operating it. And civilizations, as far as we have ever observed, are not naturally built for multi-millennial continuity of purpose. There is, however, a deeper question hiding underneath all of this, one that scientists have been quietly circling for decades, without ever fully resolving it. If interstellar and intergalactic travel are this difficult for us, they should be roughly this difficult for anyone. Any civilization, anywhere in the universe, evolving on any world, around any star, would presumably face the same fundamental constraints, the same speed limit, the same energy requirements, the same unforgiving stretch of time needed to cross meaningful distances, the same accelerating expansion of space itself working against them, which raises one of the most famous unresolved questions in all of science. A question that, on the surface, seems to have nothing to do with whether humanity can leave the Milky Way, but which turns out to be tangled up with it in a way most people never expect. In 1950, the physicist Enrico Fermi was reportedly having lunch with several colleagues at Los Alamos National Laboratory when the conversation turned, as it occasionally did among physicists in that era, to the possibility of extraterrestrial civilizations and faster-than-light travel. According to the often repeated story, Fermi listened for a while, did some rough mental arithmetic, and then asked a simple question that has haunted scientists ever since. Where is everybody? The reasoning behind the question is worth walking through carefully, because it is more rigorous than the casual phrasing suggests. Our galaxy is roughly 13 billion years old. Stars similar to our Sun have existed for most of that time. If even a small fraction of those stars host habitable planets, and if even a small fraction of those habitable planets eventually produce intelligent technological life, then over 13 billion years, there should have been ample time for at least one civilization to develop interstellar travel and begin spreading across the galaxy. Even using the slow, sublight propulsion methods this documentary has already discussed. Generation ships, multi-century voyages, gradual colonization rather than any kind of faster-than-light shortcut. Basic calculations show that a civilization spreading outward at even a tiny fraction of light speed, colonizing nearby star systems, and then launching new expeditions from each new colony, could fill the entire galaxy in something on the order of a few million to a few tens of millions of years. That sounds like an enormous span of time by human standards, and it is. But measured against the galaxy's 13 billion year history, a few tens of millions of years is a brief, almost negligible fraction. Roughly the difference between an entire calendar year and a single afternoon within it, which means that if interstellar travel, however slow and difficult, is achievable at all by anyone, anywhere, ever, the galaxy should already be saturated with the evidence of it. We should see signs, We should detect signals, structures, or simply the unmistakable fingerprints of large-scale engineering, somewhere among the hundreds of billions of stars surrounding us. And yet, after more than 60 years of organized searching, listening across the radio spectrum, scanning for unusual infrared signatures that might betray massive artificial structures, watching for anomalies in the light of distant stars, we have found nothing. No confirmed signal, no unambiguous structure, no trace, anywhere, of anyone. This silence is the Fermi paradox, and it is one of the most genuinely unsettling open questions in modern science. Precisely because every proposed resolution to it carries uncomfortable implications. Perhaps intelligent civilizations are simply extraordinarily rare, far rarer than optimistic calculations suggest, meaning we might be effectively alone, the only technological species to have ever arisen in our galaxy, at least within any window of time where evidence might still be detectable. Perhaps civilizations do arise regularly, but something reliably destroys them, or causes them to destroy themselves, before they ever develop the capacity for interstellar travel. A sobering possibility sometimes called the Great Filter, suggesting that the path from simple life to a galaxy-spanning civilization contains some catastrophic bottleneck that almost nothing successfully survives. Or, and this is the possibility most directly relevant to everything this documentary has explored so far, perhaps interstellar and intergalactic travel are simply, universally, far harder than our optimistic calculations have assumed. Perhaps every civilization that has ever existed has run into precisely the same wall this documentary has been describing. A wall built not from a lack of imagination or ambition, but from the genuine, physical, mathematical difficulty of crossing distances measured in light years using engines bound by the speed of light against a universe that is actively, continuously expanding the gaps between every unbound point within it. If that last possibility is correct, and a growing number of physicists now take it seriously rather than treating it as a fallback explanation, then the silence we observe across the galaxy is not evidence of our own cosmic loneliness. It may be evidence of a shared, universal limitation. Every civilization that has ever looked up at its own night sky and wondered whether it could someday cross the gap to another star may have eventually discovered exactly what this documentary has been carefully reconstructing over the past several minutes, that the gap is real, that it does not meaningfully shrink no matter how advanced your engineering becomes, and that the deeper you study it, the more it looks less like an obstacle to be overcome and more like a fundamental, built-in feature of how this universe is structured. This is worth pausing on because it reframes everything that follows. We are not simply asking whether humanity, specifically, with its particular level of technology in this particular century, can leave the Milky Way. We are asking a question that may apply to every civilization that has ever existed anywhere across the entire observable universe. A question about whether galaxies are, by the deep architecture of physics itself, meant to remain islands, self-contained, isolated, each one a complete universe unto itself, capable of producing stars, planets, perhaps even minds, capable of wondering about the stars beyond their reach, but never quite capable of reaching them. And if that turns out to be true, it changes the emotional shape of this entire documentary, because the story we are telling stops being a story about humanity's particular limitations and becomes a story about the universe's own peculiar architecture, about a cosmos that seems to generously scatter the ingredients for life and curiosity across hundreds of billions of galaxies, while simultaneously, almost deliberately, sealing each of those galaxies off from all the others, as if curiosity itself were always meant to outrun the body's ability to satisfy it. We have established, so far, the scale of the problem, the staggering distances involved, the physical limits of propulsion, the strange relief and burden of time dilation, the closed system and social engineering problems of multi-generational travel, and the cosmological horizon created by the accelerating expansion of space itself. We have even seen how this same wall may be silently shaping the entire visible universe, galaxy by galaxy, civilization by civilization, in the form of the Fermi paradox. But there is one more layer to this problem we have not yet touched, and it may be, in some ways, the strangest and most consequential of all. Because even if humanity solved every engineering challenge described so far, even if some future civilization built a ship capable of sustaining near-light speeds, supporting a stable, multi-generational community indefinitely, navigating successfully across tens of thousands of light years to reach the edge of our own galaxy, there remains a final obstacle waiting at the very edge of the Milky Way itself. An obstacle built not from distance, not from time, not from propulsion, but from something far stranger. The actual physical structure of galaxies, the violent, ancient environment that surrounds them, and the question of what leaving a galaxy would even mean once you actually arrived at its outer boundary. There is one more thing worth understanding before we get there, because it changes what the edge of the galaxy even means. Most people picture the Milky Way the way it appears in illustrations. A glowing spiral of stars with a clear visible boundary where the light simply stops and the darkness of intergalactic space begins. That image, as beautiful as it is incomplete in a way that turns out to matter enormously for this documentary's central question. The visible disk of the Milky Way, the stars, the gas, the dust, everything that actually produces light we can photograph, accounts for only a small fraction of the galaxy's total mass. Beginning in the 1970s, astronomers studying the rotation of spiral galaxies, including our own, noticed something that should not have been possible according to the gravity of the visible matter alone. Stars at the outer edges of galaxies were orbiting far too quickly, based on the visible mass concentrated toward the galactic center. Those outer stars should have been flung outward into intergalactic space long ago, the same way a poorly tied object flies off a spinning carousel. Instead, they stayed in stable, predictable orbits, as if something invisible were providing additional gravitational pull, holding the whole structure together, far beyond where the visible light fades out. That invisible mass is what astronomers now call dark matter, and by current estimates, it forms a vast, roughly spherical halo around our galaxy, extending far beyond the visible disk of stars, several times wider than the bright spiral most illustrations show. We do not know, even now, what dark matter is actually made of. It does not emit, absorb, or reflect light, and it interacts with ordinary matter almost exclusively through gravity, which is precisely why it remained invisible to every telescope ever built, until its gravitational fingerprints gave it away. But its presence reshapes the entire question of where the Milky Way actually ends. The edge most people imagine, the soft fading boundary of starlight, is not the true edge of our galaxy at all. It is closer to the visible tip of something far larger, far heavier, and far stranger, stretching outward into the darkness for a distance that may rival the gap between us and Andromeda itself, which means that before any future traveler reaches the genuine boundary of the Milky Way, before they cross into whatever counts as truly intergalactic space, they would first need to climb out of this enormous, invisible gravitational basin, fighting the pull of mass we still cannot directly detect, still cannot fully explain, and still cannot map with anything close to certainty. The edge of the galaxies is not a line. It is a slope, and we do not yet know exactly how long that slope is, or how steep. This is where this documentary needs to pause, and where it will pick back up. We have followed the question of leaving the Milky Way from the smallest scale. A single spacecraft, already in interstellar space, already the farthest any human creation has ever traveled. Outward through every layer of difficulty the universe has to offer. The brutal arithmetic of rocket fuel, the strange mercy and cruelty of relativistic time, the unsolved biology of multi-generational survival, the cosmic horizon carved out by an accelerating universe, and the quiet, haunting implication of a galaxy that has never once shown us evidence that anyone, anywhere, has ever solved this problem before us. And we have only just discovered that the galaxy itself, the very thing we are asking whether we could ever leave, is larger and stranger than it appears, wrapped in an invisible halo of matter we cannot see, cannot yet explain, and cannot avoid. The next part of this journey moves outward from here, into the violent, radiation-soaked environment that actually surrounds a galaxy's true edge, into the deeper physics of what dark matter and dark energy mean for any civilization's long-term future, into the question of what might happen to the Milky Way itself over the billions of years ahead, and into the most unsettling and most hopeful question this documentary has been building toward all along. If leaving is truly impossible, what does that mean for the meaning of staying? To understand what actually waits at the true edge of the Milky Way, we have to first abandon the picture most of us grew up with. The clean spiral arms, the bright core, the sense of a defined shape with a defined boundary. Like a coin sitting in the dark, that picture is real, but it is only the part of the galaxy that happens to glow. The dark matter halo surrounding it is, by most current models, roughly 10 times wider than the visible disk, and possibly more massive than every star in the galaxy combined. We are, in a very real sense, living inside a structure whose true size we cannot see, built mostly from a substance we cannot directly detect, using telescopes that can only register its presence indirectly. Through the way it bends light and herds stars into orbits that would otherwise make no sense. This is worth sitting with, because it means something uncomfortable about how confidently we can even describe the journey this documentary has been imagining. When we talked earlier about reaching Andromeda, about ships and generation crews and time dilation and a journey of millions of years, we were implicitly imagining the easy version of the question, where the galaxy's edge is the place where the visible stars thin out. In reality, that point is closer to a beginning than an end. A spacecraft passing beyond the last visible stars of the Milky Way would not be leaving the galaxy. It would be entering the long, dark, invisible outskirts of it, a region with almost no light, almost no matter dense enough to study, and almost no way for any future civilization to verify in real time exactly how far they still had left to go. It's worth pausing here to picture what that region would actually look like to anyone who somehow crossed it. Not empty in the dramatic sense of an action movie's vision of deep space, with debris fields and looming wreckage. Emptier than that, the space between the visible disk of the Milky Way and its true gravitational boundary contains scattered globular clusters, ancient, tightly packed balls of old stars, some of the oldest objects in the entire galaxy, orbiting far out in this halo like outposts on the frontier of a country whose center is millions of light years behind you. It contains thin streams of stars torn loose from smaller dwarf galaxies that the Milky Way has been slowly devouring for billions of years. Gravitational debris from a long history of cosmic cannibalism that astronomers are still mapping today, and it contains, dominating everything else by sheer volume, the invisible substance of dark matter itself. Present everywhere, detectable nowhere directly, silently dictating the orbits of everything nearby, through gravity alone. A traveler crossing this region would, in a strange way, be passing through the galaxy's memory. The scattered remains of every smaller galaxy the Milky Way has absorbed across its history, drifting in long, faint streams, like sediment suspended in still water, long after the splash that disturbed it has faded. And they would be doing so almost entirely in darkness, with the bright disk of the galaxy behind them slowly shrinking into a smudge of light, and the destination ahead of them, Andromeda or whatever lay beyond, still appearing as nothing more than a faint patch on the horizon of the sky, growing only imperceptibly larger with each passing 1,000 years. This is the point in the journey where the purely engineering question, can we build an engine fast enough, can we keep a crew alive long enough, starts to blur into something closer to a psychological and philosophical question, because the experience of crossing this halo would not resemble any journey humans have ever undertaken. It would not have landmarks. It would not have the steady psychological reward of watching a destination grow visibly closer, the way a sailor watches a coastline rise out of the horizon. For most of the voyage, nothing observable would change at all. The stars behind would fade by amounts too small to notice across a single human lifetime. The destination ahead would brighten by amounts too small to notice across a dozen lifetimes. Whatever crew, or descendants of a crew, made this journey would spend the overwhelming majority of their existence in a kind of perceptual stillness, moving, by any objective measure, at a tremendous fraction of the speed of light, while subjectively experiencing something indistinguishable from absolute cosmic stasis. There is a name some researchers and writers have used for this psychological condition, borrowed loosely from the experience of long polar air expeditions and long sea voyages in earlier human history, where crews reported a peculiar numbness that set in once the destination stopped feeling real. The sense that the journey itself becomes the only reality that exists, because everything else, the place you left, the place you're going, has receded into something closer to myth. On a multi-generational voyage across the galactic halo, this effect would not be a temporary psychological hazard to be managed for a few difficult months. It would be the permanent condition of every single person born aboard the ship who never saw Earth and would never see the destination either, their entire lives spent in the middle of a sentence whose beginning and end belonged to other people in other centuries. who they would never meet. This raises a question this documentary has been circling since the very beginning, but which deserves to be asked directly now, at the edge of the galaxy's invisible boundary. Even if every purely physical obstacle were solved, fuel, time dilation, closed ecosystems, structural durability across millennia, would the human mind and human society actually survive a journey with no landmarks, no observable progress, and no realistic hope that the people undertaking any leg of it would ever see either end of the line? We don't have a confirmed answer, because nothing remotely like this has ever been attempted. But we do have smaller, partial analogues, and they are not entirely reassuring. Long-duration isolation studies, submarine crews on extended deployments, researchers wintering over in Antarctic stations, astronauts on the International Space Station for missions stretching toward a year, consistently show measurable psychological strain building over time. Disrupted sleep, interpersonal friction, a phenomenon researchers sometimes call third quarter syndrome, where morale dips hardest, not at the beginning of an isolated mission, when novelty and purpose are strongest, and not at the very end, when the finish line is in sight, but in the long, formless middle, when the mission has stopped feeling new, and the end is still too far away to feel real. Every one of those missions lasted, at most, a handful of years, with constant communication back to Earth, with a guaranteed return date, and with crews who volunteered as adults, fully aware of what they had signed up for. A generational starship crossing the galactic halo would replicate the worst part of that psychological pattern, the formless middle, and stretch it across not months, but centuries. Worse, the people enduring the hardest stretch of that formless middle would not be volunteers who chose this life. They would be born into it, with no say in the matter, inheriting a mission they did not choose, in a vessel they cannot leave, working toward a destination they will never personally reach, on behalf of ancestors they never met and descendants they will never see arrive. This is not a detail science fiction usually dwells on, because it complicates the heroism of the journey. But it may be one of the most important practical obstacles standing between humanity and any realistic interstellar future. We have spent considerable time in this documentary discussing physics, propulsion, and cosmology, because those are the obstacles that show up cleanly in equations. The psychological and social obstacle is harder to quantify, but there is no strong reason to believe it is any less real or any less likely to be the actual point of failure for a project spanning hundreds of generations. And yet, and this is where this documentary wants to resist sliding into pure pessimism, because the story is not actually finished here. There is something almost beautiful thing hiding inside this same problem. If a multi-generational voyage of this kind were ever attempted, it would, by necessity, become one of the longest continuous human projects ever undertaken. Longer than any religion, any nation, any language has remained stable and recognizable. It would require inventing forms of culture, governance, education, and meaning-making, specifically engineered to survive across timescales no human institution has ever successfully managed. In a strange way, solving the psychological and social problem of long-duration interstellar travel might require humanity to first solve some of the deepest, most persistent problems we have never solved on Earth either. How to build institutions that outlast the people who founded them, how to transmit purpose and meaning across generations, without it curdling into dogma or dissolving into apathy. How to maintain a functioning, cooperative society without the constant external pressure of competition from other societies. If we ever manage that, if some future civilization, descended from us, actually designs a culture stable enough to survive 400 generations sealed inside a wandering vessel, it would represent, in its own right, one of the greatest achievements in the history of intelligent life, independent of whether the ship ever actually reaches its destination. The voyage might fail to deliver anyone to Andromeda, but the civilization capable of attempting it would have already proven something remarkable about what minds working together across unimaginable spans of time can actually accomplish. This is the kind of idea worth letting breathe for a moment, because it reframes everything that follows. The question of whether we can leave the galaxy turns out to be inseparable from the question of who we would have to become in order to try. But let's return for now to the physical universe itself, because there is a piece of this story that changes everything we have discussed so far. Not by making the journey easier, but by making the destination itself move. Earlier, this documentary described Andromeda, our nearest large galactic neighbor, as sitting roughly 2.5 million light-years away. That number is accurate today. But today is doing a lot of quiet work in that sentence, because Andromeda is not staying still, and neither is the Milky Way. The two galaxies are moving toward each other, pulled together by their mutual gravity, at a relative speed of roughly 250,000 miles per hour. Fast enough that, despite the staggering distance still separating them, astronomers can calculate with reasonable confidence exactly what is going to happen over the next several billion years. In roughly 4 to 4.5 billion years, the Milky Way and Andromeda will begin to collide. The word collide deserves immediate clarification, because it conjures an image of violence and destruction that does not actually match what astronomers expect to happen, at least not on the scale of individual stars and planets. Galaxies are mostly empty space. The distance between individual stars, even within a densely packed galaxy, is so enormous compared to the size of the stars themselves that when two galaxies pass through each other, the overwhelming likelihood is that no two stars will actually strike one another directly. If you shrank the Milky Way down to the size of a typical city, the stars within it would be smaller than grains of sand, scattered miles apart from one another. Two such sparse structures can pass through each other with breathtaking gentleness at the level of any individual star, even while the structures themselves, on a larger scale, become catastrophically and permanently reshaped. What actually happens, according to detailed simulations astronomers have run using our best current understanding of both galaxies' mass, structure, and trajectory, is a slow, repeated gravitational dance spanning roughly 2 billion years from first approach to final merger. The two galaxies will not strike each other once and stop. They will swing past each other, their mutual gravity distorting both structures dramatically, flinging long streamers of stars and gas out into intergalactic space before gravity pulls them back together for a second pass, then a third, each encounter closer and more disruptive than the last, until the two spiral galaxies finally lose their distinct identities entirely and merge into a single, much larger galaxy that astronomers have informally nicknamed Milky Way. A galaxy that will likely take on an entirely different shape than either of its parents, probably an elliptical structure rather than a spiral, its original disc-shaped elegance lost to the chaos of the merger. Our Sun, and whatever remains of our solar system, 4 to 5 billion years from now, will almost certainly survive this collision intact, because the odds of any direct stellar collision are so low. But the Sun's position within the galaxy will likely be flung somewhere entirely different than where it sits today, possibly ejected to a much more distant orbit within the newly merged galaxy, possibly relocated closer to its violent, reshaped core. The night sky, for any observers present to witness it, would transform dramatically over those 2 billion years. Andromeda, which currently appears as a faint, barely visible smudge to the naked eye even on the darkest nights, would grow steadily larger and brighter in the sky as the centuries passed, eventually filling a significant portion of the visible heavens before the two galaxies' structures became so intermingled that Andromeda and the Milky Way would stop being meaningful separate categories at all. Here is the detail that makes this directly relevant to everything this documentary has been building toward. The merger of the Milky Way and Andromeda is not a threat to the question of intergalactic travel. It may strangely be a kind of resolution to it. If our two galaxies are destined to merge into one single structure within the next several billion years, then the distinction this documentary has spent so long establishing, the gap between interstellar travel within our galaxy and intergalactic travel to leave it, eventually collapses on its own, not because any civilization solved the problem, but because the cosmos quietly erased the boundary by bringing the two galaxies together. This does not mean travel becomes easy. The merged galaxy would still be almost unimaginably vast, its outer regions still wrapped in the same invisible dark matter halo, its stars still separated by the same brutal interstellar distances this documentary has already described in detail. But it does suggest something genuinely worth sitting with. Over sufficiently long timescales, the universe itself sometimes does the work of bringing distant things closer together, the same way it sometimes does the work of pulling them permanently apart through accelerating cosmic expansion. The fate of any particular gap between 2 points in the universe seems to depend entirely on whether gravity or dark energy ultimately wins that particular tug of war. And which side wins depends entirely on whether the two objects in question are close enough and bound tightly enough for their mutual gravity to overcome the relentless stretching of space between everything else. This is the deepest and strangest insight this documentary has uncovered so far, and it deserves to be stated as plainly as possible. The universe is simultaneously pulling some things together forever and pushing other things apart forever. And which fate any two galaxies experience is decided permanently by gravity's reach at the moment cosmic expansion first began accelerating. The Milky Way and Andromeda happen to be close enough, bound tightly enough, for gravity to win. Most other galaxies in the universe were not. They are not our neighbors. They are, increasingly, strangers separated by a gap that grows wider every single day, with no merger, no eventual collision, no future reunion of any kind ever waiting for them. If you want to understand just how decisive this divide really is, consider the calculations cosmologists have run projecting forward not billions, but trillions of years, into a future so distant that it makes even the 4 billion year wait for the Andromeda collision look almost immediate by comparison. If the current best models of dark energy are correct, and the expansion of the universe continues accelerating indefinitely, then somewhere on the order of 100 billion years from now, every galaxy beyond our own merged local group will have already receded beyond the cosmic horizon, already moved permanently beyond any possibility of detection, let alone travel. The night sky of any far future civilization living in the merged Milky Way Andromeda galaxy would, eventually, contain nothing else. No other galaxies, no other clusters, just the stars of their own merged home, surrounded by absolute darkness in every direction. The rest of the universe having drifted entirely beyond the reach of light itself. This scenario has a name among cosmologists, sometimes called the Big Freeze, or more specifically for this particular consequence, a future of cosmic isolation. And it represents, in its own quiet way, one of the most profound predictions modern physics has ever produced. Not a violent ending, not a dramatic collapse, simply an increasing, permanent solitude as the observable universe shrinks down over inconceivable spans of time to just the one structure any future civilization happens to call home. This is worth letting land fully, because it reframes the entire premise of this documentary one more time. We began by asking whether humanity could ever leave the Milky Way. We have spent considerable time exploring the engineering, biological, and psychological reasons why that task is staggeringly difficult, even for our closest neighbor, Andromeda. But the deeper truth emerging now is this: even if every obstacle we've discussed were somehow solved, even if some impossibly advanced future civilization built ships capable of crossing millions of light years, carrying stable communities safely across hundreds of generations, the window of opportunity to reach most of the universe is not open indefinitely. It is closing, has been closing since the early life of the universe, will continue closing for the rest of time, as cosmic expansion accelerates and steadily removes more and more of the universe from the realm of the reachable, which means the real story of humanity's relationship with the wider universe may not be a story of overcoming distance through clever engineering. It may be a story of a narrowing window, a brief, cosmically early period during which a small number of nearby galaxies remain gravitationally close enough to theoretically reach, before the accelerating expansion of space permanently forecloses even those possibilities, leaving whatever civilizations exist in this era of the universe's history with one final, fixed-size neighborhood and nothing more for the rest of eternity. It's worth asking, at this point, exactly how unusual our current cosmic moment actually is. Are we living at an unusually fortunate time, early enough in the universe's history, that the local group is still gravitationally intact, still within reach of itself, before expansion has had enough time to pull everything apart? Or is this window actually quite long, by the standards of any civilization that might exist within it, stretching across enough billions of years, that the question of urgency becomes almost meaningless on any timescale a species would actually experience? The honest answer is a mixture of both, and it depends on exactly what you're asking the window to contain. The universe is currently about 13.8 billion years old. Cosmologists estimate that stars will likely continue forming at a slowly declining rate for trillions of years into the future, as galaxies gradually exhaust their reserves of star-forming gas. The window during which galaxies remain bright, active, and full of new stars. The conditions generally considered most favorable for the emergence of life and technological civilization is thought to last for a span measured in trillions of years, meaning the universe as we currently observe it, full of bright young galaxies, represents only the earliest sliver of cosmic history, not its peak or its conclusion. But the window for intergalactic travel specifically, the period during which a civilization in our position could realistically reach even its nearest gravitationally bound neighbors, is shaped by an entirely different clock. Not the lifespan of stars, but the accelerating expansion of space itself. And on that clock, we may already be living relatively late, in a cosmic sense, even though by every other measure, the universe still feels astonishingly young. Galaxies that might once have been gravitationally reachable by an early civilization, billions of years ago, may have already drifted beyond any possible future contact. The accelerating expansion has been quietly, continuously narrowing the realm of the theoretically possible since long before Earth itself ever formed, and it will continue doing so for the rest of cosmic time, regardless of whether any civilization ever notices, or cares, or tries to act before the window closes any further. This raises an uncomfortable and fascinating possibility that deserves to be stated directly. Somewhere in the universe, right now, there may be civilizations living through the exact final centuries during which a particular journey is still theoretically possible for them. The last window in which gravity still wins, just barely, against the expansion, trying to pull their nearest neighboring galaxy permanently out of reach. And there may be other civilizations in other corners of the universe who evolved too late, whose nearest neighbors had already drifted beyond the cosmic horizon, long before their species ever developed the curiosity to wonder about reaching them at all. Born into a universe that looks, to them, like the only galaxy that has ever existed, with no visible evidence that anything else is even out there. The way someone born deep inside a windowless room might never learn that an outside world exists. We do not know which category we belong to. We do not yet have precise enough measurements of the full mass and trajectory of every galaxy in our broader local supercluster to say with total confidence exactly which ones remain gravitationally reachable and which have already, silently, crossed beyond our future grasp. What we do know, with considerable confidence, is that the Milky Way and Andromeda are bound to each other, that their eventual merger is essentially certain, and that beyond that merged structure, the rest of the universe is becoming less reachable, not more, with every billion years that passes. This brings us back, finally, to the question this part of the documentary opened with, the one we deferred in order to properly understand the strange architecture of dark matter, the violent slow beauty of the coming galactic merger, and the accelerating cosmic isolation waiting in the far future. If leaving truly does become impossible for almost everything beyond our own small merged galactic neighborhood, what does that actually mean for the meaning of staying? It would be easy for a documentary like this to treat that question as a sad one, a kind of cosmic life sentence handed down to every civilization unlucky enough to evolve inside a universe built this way. But that framing misses something important about what staying actually means. Once you should understand the true scale of what we already have access to, consider, for a moment exactly what remains within reach, even in the most pessimistic version of this story. The Milky Way alone contains somewhere between 100 billion and 400 billion stars. Current estimates, built from data gathered by space telescopes, designed specifically to detect planets around other stars, suggest that the galaxy likely contains tens of billions of potentially rocky, Earth-sized worlds, an unknown but plausibly significant fraction of which may orbit within the so-called habitable zone of their star, where conditions could, in principle, support liquid water and perhaps life, even setting aside Andromeda, even setting aside every galaxy beyond our own. The Milky Way itself represents a frontier so vast that humanity, even working at the relatively modest sublight speeds this documentary has spent so much time analyzing, could spend not centuries, not millennia, but potentially millions of years simply exploring, settling, and understanding the worlds within our own galactic neighborhood, without ever needing to solve the harder problem of leaving it. This reframes the entire emotional center of this documentary's question. We began by asking whether humanity could ever leave the Milky Way, and the honest scientific answer, built carefully across everything this documentary has explored so far, leans heavily toward no. Not within any time frame that resembles a recognizable human future, and quite possibly not ever, for any civilization, given the relentless mathematics of cosmic expansion working against every journey beyond our gravitationally bound neighborhood. But the question buried beneath that answer, the one worth carrying forward into the rest of this journey, is whether no is actually the tragedy it initially sounds like, or whether it simply redirects an almost limitless ambition toward a target that, while smaller than the entire universe, remains larger than anything any civilization in history has ever actually attempted to understand, let alone explore. Before we can properly answer that, though, there is a piece of this story that demands attention, precisely because it is so often misunderstood, distorted, and oversold by popular fiction. The question of whether physics actually contains any genuine loophole around everything described so far. Wormholes, warp drives, exotic shortcuts through the fabric of space-time itself. These ideas appear constantly in popular science writing and popular fiction alike, often presented as serious, viable alternatives to the slow, grinding sublight journeys this documentary has spent so long describing. Some of them are genuinely serious physics, studied by genuinely serious researchers. Others are mathematical curiosities that technically satisfy the equations of general relativity, while requiring forms of matter and energy that may not exist anywhere in our actual universe, in any quantity, under any circumstances we currently understand. Untangling which is which, and understanding exactly why even the most promising of these ideas still runs into walls every bit as unforgiving as the ones already described, is where this documentary turns next. In 1935, Albert Einstein, working alongside the physicist Nathan Rosen, discovered something unexpected hiding inside the mathematics of general relativity, the same theory that had already revealed time dilation and the bending of light around massive objects. Their equations described a structure that seemed to connect two separate points in space-time through a kind of tunnel or bridge, cutting through the geometry of the universe rather than traveling along its surface. They were not looking for a shortcut between the stars. They were investigating the mathematical structure of black holes, And what they found, almost as a side effect, became known as the Einstein-Rosen bridge, the theoretical ancestor of what popular science would later christen the wormhole. The idea is seductive, precisely because it offers an elegant escape from everything this documentary has painstakingly established. If ordinary travel through space is bound by the speed of light, and bound by the brutal arithmetic of distance and time we've spent so long exploring, a wormhole offers something fundamentally different. Not a faster way of crossing the distance between 2 points, but a way of folding space-time itself so that the distance effectively disappears. Picture a sheet of paper representing the fabric of space, with 2 points marked far apart on its surface. Traveling between them normally means moving along the flat sheet, however long that journey takes. A wormhole, in this analogy, is what happens if you fold the paper so the 2 points touch, then poke a hole connecting them directly, allowing something to step through rather than traveling the long way around. If real, navigable wormholes existed and could be located or constructed, then the staggering distances and centuries-long journeys this documentary has described might become almost irrelevant, replaced by something closer to walking through a doorway. This is where the genuine physics and the popular imagination diverge sharply, and where scientific honesty matters more than almost anywhere else in this documentary. The mathematics of general relativity does indeed permit solutions describing wormhole-like structures. But permitting a solution mathematically, and that solution existing or being constructible in the actual physical universe, are two very different things. The original Einstein-Rosen bridge, and most of the wormhole solutions discovered since, share a catastrophic flaw. They are calculated to be unstable, collapsing and sealing themselves shut, faster than even a beam of light could cross through them, let alone a spacecraft or a living crew. In the decades since, physicists studying this problem more rigorously, including the physicist Kip Thorne, working with collaborators in the 1980s, identified a theoretical way to potentially stabilize a wormhole long enough for something to pass through, threading it with a hypothetical form of matter possessing negative energy density, sometimes called exotic matter. This is not science fiction technobabble. Negative energy density is a real, mathematically coherent concept within general relativity. And physicists have even detected tiny, fleeting analogues of negative energy effects in carefully controlled laboratory experiments involving quantum fields. But producing exotic matter in anything resembling the quantity required to stabilize a wormhole large enough and durable enough for travel remains, as far as current physics understands, not merely a difficult engineering challenge, but potentially an outright physical impossibility, depending on details about quantum field theory that remain unresolved even among specialists. Even setting that enormous obstacle aside for a moment, there is a second problem with wormholes that receives far less attention in popular discussions, and it is directly relevant to the question this documentary is actually asking. A wormhole does not eliminate distance from nothing. It requires, in essentially every serious theoretical proposal, that one end of the wormhole be constructed or discovered at the destination in the first place. You cannot dig a tunnel to a place you have never been. Someone, or something, still has to make the original journey by conventional means, carrying one end of the wormhole with them before a shortcut back becomes possible. which means wormholes, even in the most optimistic theoretical framing, do not solve the fundamental problem of reaching a previously unreached galaxy. They might, in principle, make a return trip dramatically faster after the original, brutally slow journey has already been completed by entirely conventional means. They are not a way around the wall. They are, at absolute best, a way of making one single crossing of that wall pay dividends afterward. Warp drive concepts, the other major theoretical idea frequently discussed alongside wormholes, share a similar pattern of genuine theoretical interest paired with overwhelming practical obstacles. In 1994, the physicist Miguel Alcubierre published a solution to Einstein's equations, describing a way to theoretically move a region of spacetime itself, contracting space in front of a ship and expanding it behind so that the ship sits motionless within a kind of bubble, while the bubble itself moves through the surrounding universe at an effective speed that could exceed the speed of light, without the ship ever locally violating the speed limit within its own bubble. This solution, now known as the Alcubierre drive, generated enormous excitement, precisely because it appeared to offer a mathematically legitimate way to circumvent the light speed barrier, at least in terms of effective travel time, as measured by an outside observer. But subsequent analysis revealed problems just as severe as those facing wormholes. The original Alcubierre solution requires, again, exotic matter with negative energy density, and early calculations suggested the quantity required would exceed the total mass energy of the observable universe. A number so absurd that it effectively closed the door on the concept as originally proposed. Later refinements by other physicists have proposed adjustments that reduce the required exotic matter substantially, in some versions down to merely planetary or even much smaller masses. But every refined version still depends on a form of matter that, as far as current experimental physics can determine, does not exist in usable quantities anywhere we have ever looked, and may not be producible at all given the actual laws governing our universe. There is also a more subtle problem specific to warp drives that rarely makes it into popular discussions. Even if a stable warp bubble could somehow be created and sustained, several independent theoretical analyses suggest that a ship traveling inside one would be unable to control or steer the bubble from within, unable to communicate with anyone outside it during transit, and would face the possibility of being destroyed by a catastrophic release of accumulated energy at the moment of arrival, when the bubble's structure would need to collapse. These remain active, ongoing areas of theoretical research, with real physicists continuing to publish genuine papers exploring whether any configuration might avoid these problems. But the honest, current scientific consensus is that warp drives, like wormholes, remain confined to the realm of mathematically permitted curiosities, rather than realistic engineering pathways separated from practical reality, not by a lack of imagination, but by physical requirements that may be fundamentally impossible to satisfy in the actual universe we inhabit. This is the scientific honesty this documentary has tried to follow throughout. Established fact, scientific theory, hypothesis, and speculation are not the same category of claim, and confusing them does a disservice to the genuine wonder of what we do actually know. Wormholes and warp drives are not science fiction nonsense. They emerge from rigorous mathematics within a well-tested theory of gravity. But the gap between being permitted by the equations and being achievable by any conceivable civilization may be one of the widest gaps in all of physics, wider in some ways than the gap between us and Andromeda itself, because at least the distance to Andromeda is something we can, in principle, simply spend enough time crossing. The exotic matter required for these theoretical shortcuts may not merely be difficult to produce. It may not exist as a producible substance anywhere in this universe at all, no matter how much time or cleverness or civilizational will is devoted to the search. So where does this leave the question this documentary set out to answer? Now that we have walked through propulsion, time dilation, multi-generational biology and psychology, the true scale of the galaxy's invisible halo, the coming Andromeda merger, the accelerating cosmic horizon, and the genuine but probably impassable theoretical loopholes of wormholes and warp drives, it leaves us with a picture considerably more nuanced than a simple yes or no. Leaving the Milky Way to reach distant, unbound galaxies appears to be foreclosed, almost certainly permanently, by the accelerating expansion of the universe itself. A boundary set not by our engineering, but by the deep structure of space-time, a boundary that grows tighter with every passing billion years, rather than looser. Reaching Andromeda specifically, our one gravitationally bound large neighbor, remains theoretically possible, but only by means so demanding. Millions of years of travel time, even using highly optimistic propulsion concepts. Multi-generational social and biological stability, sustained across hundreds of generations. Navigation through an invisible dark matter halo that may double or triple the effective distance involved. That it would represent, even if attempted, one of the most extraordinary undertakings any civilization could ever embark upon. And the exotic theoretical shortcuts that occasionally promise to bypass all of this entirely appear, on closer and more rigorous examination, to depend on forms of matter and energy that may simply not exist in any usable quantity anywhere in our actual universe, which means the most likely, most scientifically honest answer to the question posed by this documentary's title is this: humanity may never leave the Milky Way, not because we failed to try hard enough, not because some future breakthrough remains forever, just out of reach for lack of effort, but because the universe itself may be built at the deepest level of its physics to make this specific journey effectively impossible for any civilization anywhere, regardless of how much time or ingenuity is devoted to the attempt. And yet, before we can properly sit with that question, there is one more place this documentary needs to take us. Not outward, toward the edge of the galaxy and beyond, but inward, toward its center. Because if we are going to spend the rest of this journey arguing that the Milky Way itself, rather than the wider universe, might be the true and permanent scale of human ambition, it would be dishonest to skip past the strangest, most violent, most physics-breaking object that same galaxy actually contains. Understanding it tells us something essential about the nature of limits themselves, about what happens when a region of the universe becomes so extreme that even our best physics starts to strain at the seams. At the exact center of the Milky Way, 26,000 light-years from where you are sitting right now, there is an object astronomers have named Sagittarius A star, a supermassive black hole with a mass roughly 4 million times that of our Sun, compressed into a region of space smaller than the orbit of Mercury. For decades, its existence was inferred indirectly through the unmistakable behavior of stars near the galactic center, which were observed over years of patient tracking, whipping around an apparently empty point in space at speeds that made sense only if an object of extraordinary, invisible mass sat at the center of their orbits. In 2022, astronomers using a global network of radio telescopes called the Event Horizon Telescope finally produced a direct image of the region immediately surrounding it. Not a photograph in the ordinary sense, since the black hole itself emits no light, but an image of the glowing superheated material swirling just outside its boundary, with a dark shadow at the center marking the place where light itself cannot escape. This is worth pausing on because it represents one of the genuine triumphs of the science this documentary has been built around. An image, however faint and reconstructed through painstaking computational work, of the literal boundary beyond which the laws of physics, as we currently understand them, begin to break down. Inside that boundary, called the event horizon, gravity becomes so overwhelming that the escape velocity required to leave exceeds the speed of light itself. And since nothing can exceed the speed of light, nothing that crosses that boundary, not light, not matter, not information of any kind, can ever come back out. It would be easy to treat Sagittarius A star as simply a dangerous curiosity sitting at the center of our galaxy, an exotic hazard with no real bearing on the question of whether humanity could ever leave the Milky Way. But it actually connects to this documentary's central theme in a more direct way than it first appears. Because a black hole is, in its own right, a perfect physical demonstration of exactly the kind of boundary this documentary has spent so long describing in cosmological terms. The cosmic horizon created by the accelerating expansion of the universe, the one beyond which distant galaxies become permanently unreachable, no matter how fast anything travels, operates on a logic that is, at its core, remarkably similar to the logic of a black hole's event horizon. In both cases, the underlying cause is different. Gravity in the case of a black hole, the expansion of space itself in the case of the cosmic horizon. But the effect is structurally identical, a boundary beyond which the speed of light is no longer sufficient to escape or to arrive, no matter how that speed is achieved or by what means. This is one of the strangest and most underappreciated symmetries in modern cosmology. We tend to think of black holes as objects that trap things, and of the accelerating universe as a process that merely separates things, as though the two phenomena belonged to entirely different categories. But viewed from a slightly greater distance, both are expressions of the same underlying principle, that the universe contains real, physical, mathematically rigorous limits on what can be reached, built into the very geometry of space-time, immune to negotiation by any amount of cleverness, patience, or technological progress. A spacecraft falling past the event horizon of Sagittarius A star could not escape, no matter how powerful its engines were, because the boundary itself redefines what escape even means in that region of space-time. A signal sent toward a galaxy that has already crossed beyond our cosmic horizon could not arrive no matter how fast it traveled, because the boundary between us and that galaxy is, in its own way, expanding faster than anything could close it. Different mechanisms, same fundamental shape. The universe, it turns out, builds these absolute boundaries more than once, at more than one scale, using more than one method. as though impassibility were not an unfortunate accident of our particular circumstances, but a recurring architectural feature of reality itself. There is something almost humbling in recognizing this pattern, because it suggests that the wall, standing between humanity and the rest of the universe, is not a special insult reserved for our species, or even for galaxies in general. It is simply how this universe is built, expressed at every scale physicists have learned to examine closely enough. From the boundary of a black hole a few million miles across to the boundary of the observable universe itself, tens of billions of light years across. Limits in this universe appear to be load-bearing structural features, not unfortunate gaps waiting to be patched by sufficiently advanced engineering. And yet, Sagittarius A* also teaches this documentary something else, something that points away from despair and back toward wonder, which is, after all, the emotion this entire journey has been trying to cultivate from its opening moments. The black hole at the center of our galaxy is not simply a destroyer of things that fall into it. It is, by the current understanding of galactic evolution, intimately connected to the very existence of the galaxy surrounding it. Supermassive black holes like Sagittarius A* appear to play a crucial role in regulating star formation across an entire galaxy, periodically flaring to life as infalling matter superheats and radiates enormous amounts of energy outward, influencing the rate at which gas cools and collapses into new stars throughout the surrounding regions. The same object that represents an absolute, physics-breaking limit at its boundary may also be one of the quiet architects of the very stars, planets, and potentially life-bearing worlds scattered throughout the rest of the galaxy it anchors. This is, in miniature, the same lesson this documentary has been building toward at every larger scale we've examined. The boundaries that close off possibilities, the event horizon of a black hole, the cosmic horizon of an accelerating universe, the dark matter halo that quietly triples the effective size of any journey beyond the visible disk, are not simply obstacles standing between us and some richer existence elsewhere. They are, in a very real sense, part of the same structure that made our existence here possible in the first place. The same gravity that traps light at the heart of Sagittarius A* also helped sculpt the spiral arms in which our sun was born. The same accelerating expansion that will eventually seal off most of the universe from any future civilization is also, by some theoretical models, intimately connected to why the universe did not long ago collapse back in on itself under its own gravity, snuffing out every star, every planet, and every possibility of life before any of it had the chance to exist at all. Limits and possibilities in this universe appear to be woven from the same thread. This brings us, finally, to the question. This part of the documentary has been circling since we first turned away from the edge of the universe and back toward our own galactic neighborhood. If humanity truly is confined, for the entire foreseeable future, and quite possibly forever, to this one galaxy, and after its eventual merger with Andromeda, to this one larger, merged structure and nothing more, what does it actually mean to spend a civilization's entire existence inside a boundary this size? The instinct, especially after spending so long establishing just how absolute this boundary appears to be, is to treat the answer as fundamentally tragic. A species capable of dreaming about the stars, confined forever to a single galactic neighborhood, denied the rest of the universe. by nothing more than the unfortunate timing of its own existence, relative to the expansion rate of space-time. But this instinct, however understandable, may be built on a quiet and unexamined assumption worth challenging directly. The assumption that a single galaxy is somehow a small thing. It is worth returning, one more time, to the actual numbers, because they tend to get lost beneath the emotional weight of words like confined and boundary. The Milky Way alone contains, by current estimates, between 100 billion and 400 billion stars. If a future human civilization devoted itself patiently across thousands of generations to exploring even a modest fraction of those systems, say, one star system fully explored and characterized roughly every century, a pace not wildly different from the rate at which human civilization has explored and mapped its own planet over the past several hundred years. It would still take many millions of years to survey even a small percentage of what the galaxy actually contains. There is no real danger, on any timescale that matters to a species, of humanity running out of galaxy to explore. The boundary that closes off the rest of the universe is real and likely permanent. But the space it closes us into is not a room. It is closer to an entire ocean, vast enough that no civilization in history, however ambitious, has ever come close to mapping even its shallowest waters. There is a second, quieter point worth making here as well, one that this documentary believes deserves more attention than it typically receives in popular discussions of humanity's cosmic future. Confinement to a single galaxy is not actually a uniquely human predicament. It appears, based on everything we have discussed so far regarding the Fermi paradox, the accelerating expansion of spacetime, and the staggering practical difficulty of interstellar and intergalactic travel, to be the default condition for any civilization that might exist anywhere in the observable universe. If other intelligent species exist, scattered among other galaxies, they almost certainly face precisely the same walls we have described here. The same speed limit, the same brutal arithmetic of distance and time, the same accelerating cosmic horizon steadily narrowing what remains within reach. Whatever loneliness exists in being permanently bound to one galaxy is, in this sense, a loneliness shared by every civilization the universe has ever produced or will ever produce, which does not make the boundary any less real, but does mean that humanity, in confronting it, would not be confronting some unique cosmic injustice reserved specifically for us. We would simply be discovering, as presumably every other thinking species eventually discovers, the actual shape of the universe we all happen to share. This is, in its own way, one of the more comforting implications buried inside an otherwise sobering conclusion. The walls is not personal, it is structural, and structural limits, unlike personal ones, tend to come paired with their own internal logic, their own reasons for existing, woven into the same physics that makes everything else about the universe. Stars, planets, chemistry, life, consciousness itself. Possible in the first place. So where does this actually leave the question this documentary set out at its very beginning to answer? We have followed the problem of leaving the Milky Way from the smallest possible step. A single spacecraft, already drifting in interstellar space, already farther from home than anything human hands have ever sent, all the way out through every layer of difficulty the universe has to offer. We have measured the staggering true distances involved, not just to the nearest star, but to the edge of our own galaxy, and beyond it, to Andromeda and to galaxies that may already lie permanently beyond any future reach. We have examined the physical limits of every propulsion concept currently taken seriously by working physicists, and watched each one solve part of the problem while leaving a deeper part untouched. We have sat with the strange mercy and the strange cruelty of relativistic time dilation, which can shrink a journey for the traveler, while permanently severing their connection to everyone they left behind. We have confronted the unsolved biological and psychological challenges of any voyage long enough to require generations rather than years, and found that the hardest problems may not be mechanical at all, but human. Questions of culture, purpose, and meaning sustained across spans of time longer than any civilization has ever managed on solid ground. We have traced the accelerating expansion of the universe itself to its logical conclusion. A cosmic horizon that grows tighter with every passing era, eventually isolating every galaxy, including our own merged future home, into a solitary island, surrounded by nothing but absolute darkness. We have examined the genuine, rigorously studied theoretical loopholes, wormholes, and warp drives, and found them constrained not by a lack of imagination, but by the apparent non-existence, in any usable quantity, of the exotic matter they would require. And we have looked inward to the supermassive black hole anchoring our own galaxy's center, and discovered that the same fundamental logic of absolute, inescapable boundaries appears to operate at every scale the universe contains, woven into the same structure that makes stars, planets, and living things possible in the first place. The honest answer that emerges from all of this is not a simple no, even though no is, in nearly every practical sense, the answer the evidence currently supports. The honest answer is something closer to this. Humanity may be permanently bound to the Milky Way, and to whatever larger structure it eventually merges into, not because we lack imagination or willpower, but because the universe itself appears to be built, at the deepest level of its physics, in a way that makes this particular kind of freedom impossible for any civilization, anywhere, ever. And rather than ending that sentence in despair, this documentary wants to end this part of the journey by turning the question around one final time. If the universe has given us one galaxy, and only one galaxy to ever truly call our own, what should we actually do with it? That question, not whether we can leave, but what staying well actually requires of us, is where the final part of this journey will go. It will take us through what remains genuinely possible within the boundary the universe has drawn around us. The realistic future of interstellar travel within our own galaxy, the worlds we might actually reach, and the civilizations we might actually become along the way, the deeper philosophical weight of discovering that home was never a planet or even a star, but an entire galaxy waiting in every direction. And finally, the quiet, hard-won perspective that closes every great documentary about the cosmos. The sense that understanding our limits has not made the universe smaller, but has, if anything, revealed just how much larger the one galaxy we actually have was all along than we ever fully appreciated.